Good afternoon, physics theories. Mr. Thompson here. We're studying page 62, electromagnetic induction. We're still in our Unit 3 electromagnetism, trying to wrap things up. Let's take a look at Faraday's law. Magnetic flux can be thought of as the density of magnetic field lines that pass through a coil. So the magnetic flux shown here, there are 6 magnetic field lines that are moving through this coil. Okay? It's just illustrated with a rectangle. Faraday's law states to induce a current voltage, you must change the flux. It says, note, in order to induce the greatest voltage and thus current, you need a strong magnetic field, many loops, and you must change the flux as fast as possible. Highest rate of change. How? Well, by changing the magnetic field or by moving the loop or wire. There was this formula we used to study in Physics 30 before the change in the curriculum, and it was the induced voltage is the magnetic field times the length of wire times the speed that it's moved. Okay? So that corresponds with what here, a strong magnetic field, many loops, so a little more length of wire, and how fast it's moving. Here's Lenz's law. An induced voltage produces an induced current whose magnetic field always fights the change in magnetic flux. So it tries to oppose the change in magnetic flux. Or, simply put here, the induced magnetic force always fights the change. So in other words, provides a resistive force. Consider a magnet pushed towards a solenoid. So with Faraday's law, as the magnet gets closer, the magnetic field gets stronger in the loops. Okay? There's a change in flux in the loops, thus current is induced. Okay, so that's one way to look at it. And so the idea of magnetic flux here. So this is a magnetic field lines coming out of the north, kind of like this, simulated. Okay? Coming out of the north. And of course, you can see there's not much flux passing through the loops. But now think about when the magnet gets to be about in this position right here. I won't show the rest of it because it's in the way of the diagram, but it's moving that direction. Now, if we take a look here, there is a field line. I'm trying to make it more obvious, okay, but there is one field line there and one field line there cutting through the loops. Okay? And of course, looping back around to the other side of the magnet. So the flux is increasing through the loops as the magnet moves closer and closer. Here's how we can put it with Lenz's law. The solenoid becomes an electromagnet. The electromagnet will fight the change, in other words, repel the magnet coming in. Well, how would you repel a magnet coming in? Well, by producing a north pole to oppose it. A north pole is induced nearest the magnet, and using rule number 2, the direction of the current can be predicted. And so this is the second left-hand rule for solenoids. Okay? And so when we hold our hand, it's like this. Okay? North pole with our thumb, fingers show the current moving in the solenoid, which means it comes down, okay, on the front of the solenoid and loops back around. And that's what's shown right here. Okay? Now it states if Lenz's law was not true, then it would violate the law of conservation of energy. So what they really mean by that is if you put the North Pole in close and then a South Pole is created here, it would pull the magnet in other words, do work on the magnet, and you'd get an induced current. So you get two things. Right? In other words, you'd be creating energy. And physics doesn't work like that. All right, here's an example. Predict the direction of the induced electron flow through the galvanometer. Okay, now you're moving this magnet away. So a south pole is moving further away. Therefore, a north pole should be created to bring it back, or kind of try and attract it back. Really, an induced current is going to flow to create a magnetic field that makes moving the magnet difficult to do. Okay? Now we can use that same hand rule on the previous page. We're using our second left-hand rule for coils, and the current must be going down along the front of the solenoid, so we can show that here with some little arrows. If that's the case, it must be going along here, and it must be passing from right to left through the galvanometer. Okay? Just trying to write it down for you, okay? Sliding tube, okay? Now I put a little video. I want you to see how this works, so do check out the video I posted. I know it's about 7 minutes long, but it's well worthwhile. Why does a magnet move so slowly through an aluminum tube? Well, aluminum's a good conductor, but it certainly isn't ferromagnetic. In other words, the magnet has no attraction to the tube. So when the magnet's first dropped in, the magnet's in free fall. Acceleration is 9.81 meters per second squared, but as it increases in speed, this induces current in the aluminum tube. The induced current creates a magnetic field and force which fights the motion. The faster the magnet falls, the greater the current induced, and the greater the resistive force. Eventually, the magnet experiences balanced forces, where the magnetic force is equal to the force due to gravity, and it falls at a slow, constant speed. So you can imagine what's going to happen here, right? Down on the bottom part, we can think about the solid tube as being just made up of numerous loops, okay, of metal. North is going to oppose the north coming in, and we can use our second hand rule, like this, to figure out the induced current must go in this fashion. Now on the top, we want a north pole created here to be able to pull this magnet back, make moving the magnet difficult. And so in that case, you can see that the induced current would have to be in this fashion. Okay? Notice the currents are in different directions. We call these eddy currents. Okay? That's what the induced currents are generally called when electromagnetic induction occurs. So other examples involving Lenz's law: when a conducting rod, wire moves through a perpendicular magnetic field, a potential difference and thus a current is induced. Notice that the magnetic field is perpendicular to the length of the wire, which is perpendicular to the speed, to determine the direction of the induced electron flow around the circuit. So here's what you can think of. Here's a nice way to visualize it. You can visualize it kind of like this, using your third left-hand rule for force. Okay? So it's made up of electrons that can move in a conductor, and all these electrons are moving at a given speed in this direction. So we can use our hand rule. What we'll do is point our thumb there, we'll put our fingers into the page, showing the magnetic field, and the palm shows the force, which is towards me. And so electrons are moving down this way and will flow around the only direction they can go, which is the complete circuit. And so that makes it clockwise. In the second one here, magnetic field's coming out. This conductor's full of negative charges. Okay, it is neutral, but the protons can't move. And the speed is going to the left. And so in that case, how would I set my hand up? Well, it'd be like this, right? Fingers pointed out, thumbs pointing to the left, and the palm shows the force. Again, it means that electrons are going to be moving down here, and y will be a negative, okay? Which consequently, a lack of electrons would make x be positive, but it's asking for this as an answer. All right, when a loop of wire or any metal object enters or exits a uniform magnetic field, current is induced. Determine the direction of the induced electron flow if it exists for each situation below. Okay, entering the field, inside the field, and exiting the field. Okay, this is a different type of example and needs a different type of solution. Okay, it's not as simple as just using your third left-hand rule for force. What you need to do is you need to look at the flux. Now, as this is moving here, do you notice what's happening with the flux? So eventually, when it was further up, there was probably only 2 magnetic field lines. Now there's 4 magnetic field lines, and then eventually it's going to be 6. Okay, so 2, then 4, then 6 into the page. Okay? Now, what's really happening? It's increasing into the page. And so how does Lenz's law behave? Well, what it does is it tries to create a magnetic field that opposes that change. And so it's going to try and offset this 2, 4, 6, the fact that it's increasing, by creating a magnetic field that opposes it. And so what it does is it creates a magnetic field that's induced that comes out of the page. And here's what we can do. We know that if we use our second left-hand rule, so I'll use my second left-hand rule for solenoids. I know solenoids are lots of wraps of wire, but we can think about just as solenoid as having one loop. Okay, that's fine. And what we'll do is we'll use our thumbs up here. And so I'm going to point my thumb out of the page because that's the induced field. My hand curls around, showing the direction of the induced current. And so the current's going to be moving around this fashion. Okay? And so the electron flow should be going clockwise in this sense. Okay, now inside the field, what we're going to have here is the fact that it's 6 field lines, then it's 6 field lines, 6 field lines. There's no, okay? It says when it enters or exits a uniform magnetic field, current is induced, but when it's in the magnetic field, the uniform magnetic field, no change will happen. So there'll be no induced electron flow or current. Okay, now it's exiting the field. So let's kind of visualize what's happening here. So it's going now from 6 to 4 to 2 into the page. And so now it's starting to decrease going into the page. And so Lenz's law is going to try and offset that, oppose it, by making sure it does increase into the page. Okay? Now in this case here, what I'm going to do is I'm going to have my thumbs down. So it's going to be like this. Okay? Thumb pointed down into the page, hands curling around. And therefore the induced current will be opposite that of part A. And so the induced current is going to be counterclockwise. So this one was clockwise, this one's counterclockwise. All right, I'll stop it right there.